You're listening to Snyder & Associates webinar series, a civil engineering, planning, and design firm focused on thinking beyond engineering to improve the quality of life within the communities we serve. This episode's host is Darin Jacobs.
Hi, I'm Darin Jacobs with Snyder & Associates. I'm the Water Resources Group Leader, and we're here today to talk about disinfection system design. There are lots of different disinfection systems, and we're going to try to go over a few of them. The big problem many of you probably have in this group is that your new discharge permit requires disinfection, and probably your only real solution is to begin some sort of a disinfection program. And you're all sitting there going, wow, what do we do here? Because there's an awful lot of ways to get there. So, the first question is, how do we choose the appropriate type of disinfection? Well, one of the things that we would look at as engineers would be the technical limitation of the technology. And we'll explain this a little bit more as we go along. The cost of operation, which I'm sure the city council and your owners are all interested in. And what it really comes down to in many ways is, what is your preference as an owner? Some folks like to operate certain systems, and some people would rather do something different. Let's start off by talking about what is really available. Well, first, we have UV disinfection systems that are worldwide and are very well proven these days. We have chemical disinfection, which many of you are probably very familiar with. It includes liquid chlorination, gas chlorination, and even tablet chlorine. We have ozone, which is relatively rare, and we have chlorine dioxide, which is also relatively rare. We also have natural disinfection. And people are going to go, well, natural, can we really do that? Yeah, you can. And we'll talk a little more about that in a minute. And that could be another option for us. So, how in the world do we figure out where do we start? Well, the first thing is we need to get some test data. And we need to really test the effluent quality for transmittance if UV is being considered as an option. So, what in the world is transmittance? Transmittance is the ratio of the amount of total UV energy which can pass through the water. If you have really cloudy looking water visually, probably you're not a good candidate for UV. If the water is very, very clear, like distilled water, UV is probably an excellent option. And there are ways we can test this in the field. It doesn't have to be really complicated. So that's step one. But before we even get to that point, we've got to understand really how does this UV work? And then all of a sudden this transmittance idea is going to make some sense. Well, UV really is the light energy between about 100 and 400 nanometers of wavelength. It's a specific spectrum of light. In general, UV radiation exposure to microorganisms causes their chemical bonds to be messed up, in simple terms, and creates problems with their cellular DNA. It doesn't really kill the organism normally, but it does render them inactive or renders them unable to reproduce. We're really not that worried about a lot of these things if they can't reproduce. We're worried about them when they do get in your body and they reproduce rapidly. So really that's what we're trying to get to. This UV takes care of the internal components in their cells. I thought this was kind of a neat photo that shows DNA helix damage from UV radiation. And you see the broken pieces of the DNA helix, and that cell might survive for a while, but it's never going to be able to reproduce. So we should always try to test your transmittance at a high flow condition and a low flow condition, as water clarity can vary considerably, as I'm sure all of you can attest. When you have that first flush with a 4-inch rain, anything and everything gets washed out of the sewer. What do you think is going to happen to your UV transmittance values? Probably not as good. At low flows, probably you have pretty good values, although I've been to plants where low flows cause problems and they don't have very good transmittance values. Generally speaking, however, effluent will be clearer, providing higher transmittance values at higher flows than at low flows. And it's usually due to rainwater. Anybody have leaky sewers? Yeah, most of us have seen that. So how much energy is required if we do use UV? Let's pick a few important ones. How about cryptosporidium? We all know that that's a particularly difficult organism. And you can see that there are values there that we have to meet. And crypto for a 2-log effectiveness is about 330 milliwatt seconds per square centimeter. That's kind of an odd sort of units, but remember that number, 330, because in a minute we're going to talk about what we really dose things with. And you'll notice that's the highest one on the list. How does that relate to my process? Well, generally speaking, the minimum UV transmittance threshold we would normally want is about 45%. More is better. If we're in the 60s, that's great. 45 is about the bottom line. And you'll notice that in a non-aerated lagoon, oftentimes we're down around the 30 range. You can see by comparison, drinking water is nearly 100. A number of people probably have activated sludge, and UV works very well with activated sludge, and you can see why using this graph. Usually that's around 65, maybe even 70%. So UV is particularly well suited for that. What affects our UV transmittance? Well, BOD, COD, TOC really doesn't have much of an effect at all. And I wouldn't say we can ignore it, but it's pretty not substantial. Humic materials are very strong absorbers of UV radiation. And guess what? A lot of wastewater has high humic material content. The other one that's a big deal is hardness. Now, I know nobody in the Midwest particularly has hard water, but remember, even though that water's been through the water treatment plant on the drinking water end, probably the filter backwash and other things have found their way to the wastewater end. So calcium, magnesium, any kind of salts, they will oftentimes provide the ability to put really strong deposits on your UV quartz tubes, especially when you elevate the temperature. Guess what happens inside those tubes when we are running UV light? Elevated temperatures. There's a lot of things that can affect transmittance, and it's something you got to keep your eye on when selecting a process. How about nitrate? Yeah, really no big deal. Nitrate is clear, doesn't have an effect. Iron. Iron is a problem. And how many water systems in the US and North America have iron? Most of them. Iron is a very strong absorber of UV radiation. It can precipitate on those quartz tubes, and it can also provide shielding for those bacteria. Manganese, the other nemesis of our water systems, is also a strong absorber of UV radiation and can cause lots of trouble. Go down to industrial discharges. Oftentimes we see colorants, we see dyes. That can be a real problem as well. I know that many people don't have industry or have limited exposure, but industries can really cause a lot of trouble with this. So how in the world do we test effluents for transmittance? Well, we have a small device and we can take a sample of the wastewater and it tells us what the percentage is. The device is normally compared against distilled water, so nothing complicated. Many of us have these, and this is step one. So now we've tested the effluent quality for transmittance, and if the transmittance is less than about 45%, probably this is a good time to think that UV may not be the right option. If your transmittance is greater than 45%, UV probably is a viable option. We're not done testing for UV yet. There's one more test that oftentimes comes into play. It's called the collimated beam test. If we first find out that UV is potential because of transmittance, we still need to run this collimated beam. The collimated beam really needs to be performed, especially for suspect or particularly difficult wastewater, maybe industry or something similar. You can get some unexpected diffraction through the water column, even though it appears to be very clear, and that can cause real problems. The collimated beam test is actually used to develop a dosage curve, and in this curve, it verifies how much UV is really required to do the job. And again, this test is run on a sample of the wastewater that is actually to be treated. Most manufacturers of UV systems can do this. This is a much more complicated test, so the ability to do it in the field is probably not there. So when you run the collimated beam, you get a curve that shows the survival and it shows the effective UV dose. And you can see that the more UV we put in, the lower the survival rate. And that's shown on the graph here. Now we're back to our table. We have said that our transmittance value is less than 45%. So UV is not a viable option. If we go the other way and we've decided UV might be viable, now we take that collimated beam test, and if we get successful values, UV might be a good fit. But if the collimated beam fails, probably it is not a good fit, and the thought for UV probably ought to be discontinued at this point. So now, some rules of thumb. Everything on these previous slides are really rules of thumb. They're not really rules to live by. That means that you may have a manufacturer that can deal with the wastewater that you have. So don't write it off until you have a good talk about it. UV has really been successfully installed on almost every type of process and has been unsuccessful in that process, at the same time being successful somewhere else. So work with your manufacturer and your engineer to figure out how that goes together. More rules of thumb. A lagoon system is often much more subject to variable UVT. What happens on a windy day? When you have a really windy day, probably your UVT is low in your lagoon system, right? How about when the algae is growing in the middle of summer? Probably low UVT. Lagoons followed by a Sager system, for example, are usually much better than a lagoon treatment by itself. Now here's a big one, and this might be a rule to live by. Each 5% increase in UVT results in about 20% more equipment. So if the UVT value is lower by 5%, you get about 20% more equipment, and probably about that much more in energy use. That's a big deal. A TSS of less than 25 to 30 is a lot better than a high TSS. Remember, we were talking about humic material being a big absorber? Guess what? That's what a lot of your TSS probably is. Your iron less than about 0.3, manganese less than 0.05, and if you can get a hardness of less than 400, that's probably a reasonable number. Remember again that even if you soften your water, you most likely get the filter backwash and other residuals at the wastewater plant. So really in the end, you don't lose that when it comes out of your well field or out of your surface water source. Color can affect UVT. Oftentimes, some colors have a greater effect than others. Use of chemicals upstream, like ferric chloride, can affect UVT. Many of you may have industries that apply ferric chloride to their process. Some of you may even use ferric chloride in your own process. So that one's a big one. And remember, it's the iron that's the big deal. All tubes will need to be cleaned. It's just a matter of how often. More frequently cleaning the tubes may be required in warmer months, or if you live in a warmer climate because you have a lot more algae growth. So I'm going to refer to the Iowa DNR on these regulations just because they have a really well-written standard. Most other states have standards that are very similar and oftentimes are identical. So if you remember, ultraviolet radiation in Iowa, we have to have a minimum dosage of 16,000 microwatt seconds per square centimeter at every point in the wastewater disinfection chamber. You remember what the number was for cryptosporidium? It was 333. That's a huge difference between 16,000 and the 333. So you can see that we are very strongly dosing this water to make sure we get that kill of the organism. Most manufacturers would agree with number two. The maximum water depth in the chamber between tube surfaces shall not be greater than 3 inches for low intensity units, 8 inches for high. Again, the different states have somewhat different standards, but this is kind of an industry-wide thing. The key items I kind of picked out of the Iowa DNR standard. The unit will be designed to permit frequent mechanical, chemical, or ultrasonic cleaning of the water contact surface of the jacket without assembly of the unit. Okay, remember we talked about every UV system is going to need to be cleaned. Well, it needs to be reasonably convenient to clean it. Let's face it, if it's not convenient, we're never going to do it, and we're not going to be successful. So it's got to be a good thing, and it's got to be easy. We also have to have an adequate number of intensity meters. Most every manufacturer installs automatically in their system a UV intensity meter that will send an alarm when the intensity drops off, either because UVT dropped or because the tubes are dirty or maybe you have some bulb failures. Where disinfection is required for a whole year, which is somewhat rare in the upper Midwest, the design must be provided so that with the largest unit out of service, all of the remaining units would have the capacity to handle the peak hour wet weather flow in Iowa. Every state has a similar kind of regulation. Iowa maybe words it a little differently, but most every state has the same kind of regulation. In a nutshell, when you have your highest flow, you need to be able to take that largest unit out of service and still meet the requirement. In the state of Iowa and most other states, you really need to have some sort of a portable unit to go out and check and make sure that the permanent detection units for UV are doing their job. And it's important to have this regardless of state reg. It is a good practice. Your operators always need to walk out and double check that this is doing its job. It's simple, it's readily available today, and most manufacturers will send this with their product as part of the lab equipment that you get at your plant. So, what does a typical disinfection system that uses UV look like? Well, there's a contact variety and a non-contact variety. For contact variety, the wastewater generally surrounds the lamps, and the lamps are protected inside quart sleeves. With non contact, water tends to flow through clear tubes that are surrounded by UV lamps. The UV lamps are actually in the dry, so the tubes are touching the water. And we'll look at a couple of these in a second here. Here's a picture of what those units kind of look like. You can see there's a box here, and the units are vertical and they stick down into the channel. There's one that you can really see the tube laying in the water, and you can even see the UV energy being imparted into the water. The funny looking finger thing is actually a finger weir, which provides a lot more length so that the water level really doesn't change very much based on flow rate. And you'll see that in a lot of UV systems. More of a very similar kind. This one is an in-channel system. You can see the boxes up above and it sticks down into the channel. And if you look to the right photo, you can see quart sleeve with a UV bulb inside being pulled out by an operator. On this slide, you can see some UV systems even go inside of a pipe. Tubes oftentimes go in sideways. In this case, they're lengthwise. You can see there's a pipe connection where the water goes in, pipe connection where the water comes out. The typical large system for contact looks a lot like these photos. On the right photo, toward the middle, you can see there's large cartridges that are loaded with UV tubes. This one has low pressure, high output lamps with automated cleaning. This one was designed for an installation of about 2.5 mgd or larger. In this case, 10 to 12 lamps are probably used per mgd. You can see smaller versions. They don't all have to be huge. You can see the horizontal cartridges in both of these photos. You can see probably better in these photos how a horizontal works. In this case, this is a non-contact horizontal unit. The water flows through a tube and the bulbs fit between the tubes. That way, each tube gets exposed to ultraviolet light from all sides. And quite honestly, these have produced much better results than average in places where you have coloration in the water, because you can pretty much always guarantee that the water is being exposed to an adequate amount of energy. Here's kind of a cartoonish drawing of how that looks. The lamps are in purple, flow is in blue, and you can see that the lamps are in the dry, which has some advantages, and the water flows in between. In a contact unit, which is the top unit, you can see the water is actually touching the tubes. So it's quite the opposite in a non-contact. The water flows through the pipe, the lamps sit in the dry. Here happens to be a typical non-contact horizontal unit, and you can see that it is simply installed on a concrete pad, and it actually sits outside. Here you can see, much like the horizontal contact units, the UV tubes are in racks, and you can pull a rack and change the rack or its tubes and put it back in place. You can see one in operation in this photo, and you can see the water in this case is only coming out of the bottom few tubes. So there's no real reason to turn the UV on above about the second tube. Therefore, we can save some energy. And that has to do with being flow paced. It's nice and easy to flow pace this type of a model. The other models also can be flow paced. And again, it's oftentimes used to disinfect particularly difficult water where you have caramel coloring, dyes, things like that. So, what in the world is the advantage of a UV system or the disadvantage of it? Well, an advantage of UV, it's a very effective disinfectant. It takes out bacteria and it effectively takes out viruses. Oftentimes, chlorine will not successfully deactivate a virus in the time that we allow it to be in contact, but UV will. The nice thing with UV, there's no residual toxicity. How many people out there have to run total residual chlorine test in their effluent water because the EPA, the DNR, the DEQ of your state wants you to make sure there's no chlorine getting into the receiving stream? Well, with UV, that doesn't exist. It's much more effective, as I just said, in inactivating viruses, spores, and cysts. It doesn't make DPBs. Disinfection byproducts are a problem, and everybody is very much aware of them. It also doesn't increase TDS in the level of your treated effluent, and that can be a big deal for those who have TDS limits. So, what in the world are the disadvantages? This seems like a no-brainer. Well, part of the problem is there's no immediate measure of whether or not it was successful. You won't know for a few days when you take your test that you actually were successful at disinfecting. With chlorine, as long as we have chlorine remaining, we were successful. We know we were. There is no residual to check. It is somewhat less effective in inactivating some viruses and cysts at low dosages. So we want to make sure we get an adequate dose. It's more energy intensive, as is pretty obvious. If you already have energy problems, like no power at your site, this may not work out very well. And the hydraulic design of the UV system is absolutely critical. We talked about those finger weirs, very important. A lot of people today are getting chloride limits in their NPDS. The beauty of UV, it does not affect your chlorides. Chlorine will, but UV will not. Oftentimes, people review UV as having improved safety when compared to chemical disinfectants. I would argue that to some degree. If you get exposed to that UV, it can cause blindness and a lot of other issues. So, making sure that the UV is used properly is a big deal, much like it's a big deal to make sure that chlorine is used properly. It often requires less space than chlorine. You can see those cartridges were pretty small, not requiring a lot of floor space. The other advantage, at high UV dosages, much higher than those required for disinfection, UV can be used to reduce the concentration of trace organics, such as NDMA, which is a really, really long name for a semi-volatile organic chemical that's really highly toxic. Many of our water systems in North America and the Midwest, oftentimes you find things like atrazine, which is an organic, and UV can effectively reduce that. So the other disadvantages, relatively it's expensive. Although the price has come down over the years and technology is improving and it's reducing energy use and it's reducing expense. It takes a relatively large number of UV lamps where low pressure intensity systems are specified. Oftentimes, it requires acid washing to remove scale buildup, and lack of a chemical system oftentimes has other issues at a wastewater plant, such as your ability to control odor. We often use chlorine for disinfection of internal plant systems. And in this case, we wouldn't have that. So going back to where we started, we're going to go up the other way. If transmittance is less than a 45%, we're going to have to go to a non-UV system as a more appropriate choice. In some cases, we can actually get natural disinfection. I have personally done this and been successful at it in a short term. It was more of an emergency situation than a long-term solution. But generally speaking, natural disinfection can be successfully achieved. It occurs via sunlight. What does sunlight have in it? Oh, yeah, UV. It also results from microbial die off due to lack of food. Normally, though, we got to hold that effluent for about 30 days. And by contrast, if this was a system treating 100,000 gallons a day, which is not a big system, you would have to have a lagoon approximately 1.5 acres in area and 6 feet deep. So very large. The effectiveness is also really controlled by turbidity of the wastewater, suspended solids, pH, on and on and on. Most EPA, DNR, DEQs generally do not have a standard for this type of design, although everybody knows it can work. This is another option maybe for natural disinfection. A lot of you have heard of SAGR, the Submerged Attached Growth Reactor System. And right now, SAGR is going through testing to see if they can naturally disinfect, thereby reducing the need for UV or chemicals such as chlorine. So the big deal with natural disinfection, obviously it has some advantages. Doesn't really need a lot of oversight, doesn't need much maintenance, little if any power cost, it really doesn't have any chemical cost to speak of. But the downside, lack of predictable results. We can't guarantee that we're going to meet the requirement. And most regulating agencies require that we meet the requirement every day, and we can't do that with natural disinfection. It's easily upset by changes in the environment. What happens if the wind comes along and blows leaves and dirt into the system? So the Biggest problem with this is lack of predictable results. If we determine that really we can't guarantee natural disinfection, we have to go to something that is chemical. And there's a couple common types of chemical disinfection. There's gas chlorine, liquid chlorine, which is usually sodium or calcium hypochlorite, and possibly tablets. So we're back to the Iowa DNR standard, but most states have similar standards. It says that the disinfectant must be positively mixed rapidly as possible. Okay, the important part of this can be accomplished by the use of a turbulent flow regime, a hydraulic jump, a mechanical mixer, or a jet disinfection system. Basically, what it says is we got to mix it, and we got to mix it effectively. Now, here's the other piece of this. We've got to have contact time. We've got to have a minimum period of 30 minutes of detention at high flows. In the case of Iowa, that's average wet weather and peak hourly wet weather. And every state has a standard like this. In a nutshell, it means a long disinfection period. The contact tank of these things can be large. Most systems are required by their state regulators to use something on the order of a baffled 40-to-1 length to width ratio tank. That's a sizable tank. And most states require duplicate tanks so that if either one of them is out of service, the other one can provide the application of the chlorine. How much chlorine do we really have to do if we're going to disinfect? Well, if this is primary effluent, probably something on the order of 15 milligrams per liter. Trickling filter, you'll note, is about 10, and every plant's different, as we all know, but this is kind of a guide. Activated sludge doesn't require as much at about 8. The more treated we get, the lower the amount of dosage generally. Here's a picture of a typical concrete chlorine contact tank. You'll notice the long, narrow pathways that are baffled, and it is a large and expensive tank. We've been doing those contact tanks for many years. This is a process that used actually a jet chlorination system that has been in for many years. By doing so, they were able to get away with a lot shorter tank and a lot shorter and smaller concrete overall tank. The jet disinfection is right at the beginning. It pulls in the chlorine, it adequately mixes the water, and by doing so, we have an effective kill in a much shorter amount of time. Many states require a variance for something like this to be built, but it does work. So many of you do not run systems that are huge, and you don't need UV disinfection, or you don't need liquid or gas, chlorine. So are there other options? Well, yes, there is. One of the options that we've successfully used in a few locations have been a tablet feeder. Many systems are out in a location where there is no power or very limited amounts of power electrically. This thing doesn't even need power. You load each one of those tubes up with very large pellets, and over time they dissolve into the water stream. You see how it's in the flow stream and exposes the chlorine as required and gives you a chlorine source. Let's talk about advantages and disadvantages of chlorination and chlorine disinfection systems. Well, it's a well-established technology, and quite honestly, I have great faith in its ability to do the work. Even when your plant isn't running very well and your effluent looks terrible and UV could never do the job, chlorine can do the job. Normally, you might feed 2 milligrams per liter, but if it won't make the requirement at 2, okay, we can feed 10, whatever it takes. It's a very effective disinfectant. It's easy to maintain, and most of us know how to do that because we do it on the water side as well. We could make a combined chlorine residual if we want. There's just a lot of advantages in that method. The availability of chemical system for other uses, such as we talked earlier, odor control, that's also a nice advantage if you already have chlorine on the site. In addition, the advantage from chlorine, we said, is relatively inexpensive. Well, sort of. The cost of the chlorine is inexpensive. The cost of the equipment is inexpensive. The cost of the concrete tank is quite expensive. You have multiple options too with chlorine. You can get calcium hypochlorite, sodium hypochlorite, chlorine gas, on and on and on. Now, most people would say, well, yeah, but there's some disadvantages to this too, and they're correct. Chlorine is a hazardous chemical, and it can be a threat to plant workers and the public. So that is a problem. It takes a relatively long contact time to be effective, as you can see by the size of those concrete tanks. The important part also is the formation potentially of trihalomethanes and other disinfection byproducts. It also tends to release volatile organic compounds from chlorine contact basins. Back to the iron and magnesium, manganese, things like that, the chlorine will tend to oxidize these chemicals. And when that happens, it does consume your disinfectant. And again, we talked about everyone probably has iron in their water in some form. The TDS of the effluent treated is often increased by chlorine systems. The chloride content is also often increased. And that is a problem for a number of people who have chloride limits in their effluent permit. So there are a number of things that aren't always perfect. Generally, if a chlorine system is used, you're always going to have to do dechlorination. Dechlorination must be provided to make sure that we're not putting chlorine out into the receiving stream. Dichlorochemicals have to be rapidly mixed with the effluent in order to be effective. Sulfur dioxide dichlorination systems shall be designed with the same equipment as the chlorine systems for maximum interchangeability. I always found that one to be kind of interesting. Oftentimes we need effluent reaeration after dechlor because we've taken apart the dissolved oxygen in some cases and need to ensure that it has been returned. We also need to monitor the effluent residual to make sure that we meet the discharge permit requirements. Dechlor is required by most all NPDES permits, which are ultimately overseen by the EPA, so it really doesn't matter which state you're in. Generally speaking, dechlor can be easily accomplished with the addition of sulfur chemicals like sodium bisulfite, sodium metabisulfite, sulfur dioxide. So, a much less popular chemical disinfection system is ozone. There are a few ozone systems around. It seems like oftentimes they were much more popular back in the 1970s than they are today. Although that's a pretty generalized statement, I think that's fairly true. So, key Iowa design requirements, again, common with many other states. The ozone is really not that different from chlorine gas. It's produced on site and then it's put in solution on that site. And you're going to note a lot of things here that are very similar. You notice that it takes a long and large concrete contact tank. Again, the baffled length, 40-to-1 ratio. Remember that from the chlorine side? Same thing. Duplicate tanks are required, same as chlorine. So we really didn't change anything between those two chemicals. And general advantages of ozone. It is a very effective disinfectant. It requires a lot of equipment, and it is very effective in deactivating viruses, spores, cysts. It also, in theory, requires less contact time. However, you'll note that the standards for most states are not written to accommodate that. Again, we're back to the disadvantages. We have no immediate measure of whether or not it was successful. Maybe it was, maybe it wasn't. There's no real way to tell. From that standpoint, the other disadvantages, it's often energy intensive because it requires a lot of electrical power to generate the ozone. And typically it's an expensive system. So you just don't see a whole lot of these. So to sum it all up today, as you can see, there are a lot of options for meeting your disinfection requirements. If you should have any questions, please feel free to reach out and we will try to answer them.
Thank you for listening to Snyder & Associates webinar series, a civil engineering, planning, and design firm focused on thinking beyond engineering to improve quality of life within the communities we serve. Find content related to this episode on Snyder-Associates.com.